Let's take a look at Euler's formula by Hannah Shaley. First, we will dive into what is Euler's formula. Next, we will go into a formula breakdown, and last, real-life scenarios. Euler's formula is a very famous theorem. Euler's formula was named after the mathematic legend Leonhard Euler. Euler's formula lives in the world of complex numbers, specifically when introduced to trigonometric expressions. Euler's formula bridges the relationship between trigonometric functions and exponential functions into the same plane. Back in the 1800s, mathematicians were unable to comprehend the formula, but knew it to be true because they proved it so. Today we understand it much better. Let's dive into it. There are two concepts that go into the basic form of Euler's formula. E is a big part of Euler's formula. When you perform differential equations, e to the x is the solution. This is because when you take the derivative of e to x, the solution is e to x, as shown below. We do the same in Euler's formula. Similarly, when you take e to the ax, it equals a e to the ax. The property is when you take the derivative of the function, the same function comes out. There are also sinusoids, such as sine and cosine, which are also a large part of Euler's formula. These things occur in nature, such as when you hear a bell, it will move in a sine wave. This equation uses sinusoidal variations including AC currents, sound waves, and basically all vibration. Cosine x is the horizontal distance, and I sine x is the imaginary vertical distance. We will work these two concepts together to understand Euler's formula. Here is the formula breakdown of the complex analysis. You have I to the x equaling cosine x plus I multiplied by sine x. E is Euler's constant, which is approximate to 2.71828. This is the base of the natural logarithm. You also have I, which is the imaginary unit. It is a complex number. Imaginary numbers rotate around a plane, opposite of cosine and sine. This is the square root of -1. X is the real number in the equation, and is measured in radians. Last, you have cosine and sine, which are ratios of a right triangle that come out of the unit circle. In your complex analysis equation, cosine x is the real part of the equation, while the I multiplied by sine x is imaginary. Euler's formula comes from the base of e to the x equals cosine x plus sine x. Euler's formula adds in the imaginary number I. Now you have e to the ix. To make it easier to understand, you can break it out into a polynomial expansion, breaking out cosine x and I sine x. Once expanded, it does prove that you could input in an infinite amount of numbers and that all will equal cosine x plus I multiplied by sine x. So let's look into what this formula has to offer farther. Next, we have Euler's identity, which is a breakoff from the original formula. This is just when x is replaced by pi, leading us to the formula e up to the I pi equals cosine pi plus I multiplied by sine pi. While Euler's formula is used to help calculate e to an imaginary power, Euler's identity is used to show how the constants e, pi, and I are related. Mathematicians call Euler's identity a mathematical beauty because it includes 5 mathematical constants. Like stated before, 0, 1, e, I, and pi are all used exactly once. And this equation also uses addition, exponential, and multiplication exactly once. This is also described as a simple and cohesive equation in the math community. You may be wondering what the overall goal of the last two equations are. Euler's formula gives us another way to describe motion in a circle. Even though we could already prove it with sine and cosine, if you were asking a math lover what the big deal was, they would tell you it's all about perspective. Cosine and sine describe motion in terms of a grid, plotted through horizontal and vertical coordinates. Using Euler's formula, you use angles and distance along with polar coordinates. This is giving you an angle that rotates around the circle, going x units at an angle of x degrees. We will now break down the formula for a polyhedral of Euler's formula. Polyhedrals are 3D solid shapes whose surfaces are flat and whose edges are straight. For example, a cube, prism, pyramid, sphere, etc. For any polyhedron that does not self-intersect, the number of faces, vertices, and edges are related in a particular way. Euler's formula for polyhedrals tells us that the number of vertices and faces together is exactly 2 more than the number of edges. Euler's formula is F plus V minus E equals 2, where F represents the number of faces, V represents the number of vertices, E represents the number of edges, all equaling 2. The purpose of this formula is to find the relationship between the number of vertices and edges that will assist in problem solving in regards to the surface used. This formula is not only used for 3D shapes, but it can also be used for three-dimensional space. Let's now look into an example problem. This question states, suppose you have a solid having only triangles and squares as faces. Suppose that the degree of each vertex is 4. Prove that the solid must contain 8 triangles. First, you would ask yourself, what are you trying to solve here? You realize that you are going to need to use the polyhedral Euler's formula in order to complete this assignment. Thanks to Muralid Haran for the full explanation, we have the answer here. We would let m be the number of triangles and n be the number of squares. The total number of vertices is 3m plus 4n equals 2e, since each edge will be counted twice and the number of faces is m plus n. By Euler's formula, we now have v minus e plus f equals 2. We substitute our numbers in, which would be 3m plus 4n over 4 minus 3m plus 4n over 2 plus m plus n equals 2. This will then give us m over 4 equals 2, then allowing us to get the triangles of m equaling 8. This then proves that, yes, the solid must contain exactly 8 triangles. Let's move on to a real-world example for the complex analysis. The complex analysis and, along with the other formula of polyhedra, are both used in real-world examples a lot. Let's start this example by looking at your phone. Now look at your computer. Now turn to your TV. All of these electronic devices and more deal with alternative currents, or AC. In math, AC is treated as a complex wave. Using Euler's formula, it makes a simple way to account for the behavior of electric circuits using AC. Let's take a look at an electrical engineer. He is working away with AC or alternative currents. But he runs into an issue. Electrical engineers choose AC over DC typically because they are cheaper and have a fewer energy loss due to the direction changes of current. As a reminder, Euler's formula relates the complex exponentials to the cosine and sine functions. This formula is very important to the AC analysis. It is why electrical engineers must understand complex numbers. Like we said, he ran into an issue in the circuit. Luckily, Euler's formula can be used to simplify issues within the circuit. Otherwise, the engineer would have to use differential equations, and many of them, to work out a simple circuit problem. The results are resistors being real values. Resistors allow an amount of current directly proportional to the voltage to be parallel at all times. Inductors are positive imaginaries. Inductors control and decrease current without power loss. And capacitors are negative imaginaries, which improve the power factor. Once you use Euler's formula to complete it, you run AC currents through them and real and imaginary voltage results. The engineer has ended up in a happy result, and he didn't have to take the extra steps to complete a simple task, and the cycle continues. As you can see, Euler's formula is a rare gem in the realm of mathematics. It establishes the fundamental relationship between exponential and trigonometric functions and paves the way for much development in the world of complex numbers, complex function, and related theory. Thank you so much for listening, and I hope you learned some more about Euler's formula. Thank you.